nuclear space engine backed by NASA could fly humans to Mars in just 45 days. Overview. NASA is taking significant strides towards enabling crewed missions to Mars with the development of a nuclear space engine that has the potential to drastically reduce travel time to the Red Planet. This initiative, known as the Demonstration Rocket for Agile Cislunar Operations DRACO, is a collaborative effort involving NASA, the Defense Advanced Research Projects Agency DARPA, and several industry partners including Lockheed Martin and BWX Technologies. The goal is to test a nuclear thermal rocket engine in space with plans for a demonstration as early as 2027. Key developments and timeline. 1. Historical context. The idea of nuclear propulsion has been around since the 1950s but was largely abandoned in the 1970s due to budget constraints. The recent renewed interest stems from advancements in materials and engineering which make the current efforts more viable. 2. Partnerships established. In January 2023, NASA and DARPA formalized their collaboration to advance the DRACO program. This partnership delineates roles and responsibilities aiming to speed up the development of nuclear thermal propulsion technology. 3. Technical goals. The nuclear engine being developed is expected to cut the travel time to Mars from approximately 7 months to around 45 days. This is achieved through a propulsion system that is potentially 3 times more efficient than traditional chemical rockets. The engine will utilize a fission reactor to heat liquid hydrogen, which is expelled to generate thrust. 4. Testing plans. The first test of the nuclear thermal engine is scheduled for 2027. The initial flight will involve the rocket demonstrating its propulsion capabilities at altitudes ranging from 435 to 1,240 miles. For safety purposes, the reactor will remain off until the vehicle reaches orbit. Common themes across sources. Time reduction. All reports agree on the significant reduction in travel time to Mars, estimating it at around 45 days with nuclear propulsion. Efficiency. The nuclear thermal rocket is noted for its superior efficiency compared to chemical propulsion, with claims that it could be up to 3 times more efficient. Collaborative efforts. The partnerships between NASA, DARPA, and private companies like Lockheed Martin and BWX Technologies are emphasized in all discussions surrounding the DRACO program. Different perspectives. While the core goal of reducing travel time to Mars remains consistent, different sources highlight varying aspects of the technology. Technological focus. One source discusses the nuclear electric propulsion system being developed by Space Nuclear Power Corporation SpaceNukes, which aims to enhance maneuverability and efficiency, while other reports center on the nuclear thermal rocket that Lockheed Martin is set to test. Funding challenges. Some sources, like the one from Interesting Engineering, note the difficulties faced by companies like Ad Astra Rocket Company in securing funding for nuclear propulsion projects, indicating broader financial challenges in the sector. Use cases and implications. The introduction of nuclear thermal propulsion not only promises to reduce transit times but also has significant implications for astronaut safety and mission logistics. Shorter travel durations lead to a decrease in required supplies and systems for long-duration missions, making crewed flights to Mars more feasible and less risky. Conclusion. NASA's initiative to develop a nuclear space engine marks a significant advancement in space travel technology, focusing on efficiency, speed, and safety for future Mars missions. The planned tests in 2027 will be critical in demonstrating the viability of this technology, potentially ushering in a new era of human space exploration. Detailed event report. Initial research and context. The journey towards a nuclear thermal rocket began decades ago, with significant research conducted in the 1950s under the Nuclear Engine for Rocket Vehicle Application (NERVA) program. However, political and budgetary challenges in the 1970s led to the suspension of nuclear propulsion projects. The current resurgence is fueled by advancements in aerospace engineering and materials that allow for safer and more effective nuclear propulsion systems. Formation of partnerships. The partnership between NASA and DARPA was announced in January 2023, marking a strategic collaboration aimed at propelling the DRACO program forward. This agreement is designed to leverage the strengths and resources of both agencies to hasten the development of nuclear thermal propulsion technology. NASA brings its extensive experience in space missions, while DARPA contributes its expertise in advanced technology development. Pam Melroy, NASA's deputy administrator, emphasized the importance of this collaboration, stating that it would accelerate the technology development necessary for sending humans to Mars. This partnership is expected to yield significant advancements in propulsion technology essential for deep space exploration. Technical goals of the nuclear engine. The nuclear engine's design focuses on efficiency and thrust. Conventional chemical rockets operate by burning fuel in a combustion chamber which produces thrust through the rapid expulsion of gases. In contrast, a nuclear thermal rocket generates thrust by heating a propellant, in this case liquid hydrogen, using a nuclear fission reactor. This method not only increases efficiency but also allows for higher thrust capabilities, enabling faster travel times. The projected travel time reduction from 7 months to approximately 45 days represents a substantial leap in human space exploration capabilities. This enhancement not only addresses the logistical challenges of long-duration space travel but also reduces the overall risk to astronauts by minimizing their exposure to space radiation and the psychological strains associated with extended missions. Testing and demonstration plans. The initial test for the DRACO program is planned for 2027. During this test, the nuclear thermal engine will not operate its reactor until the vehicle reaches a safe orbital altitude. This precaution ensures that the technology is tested in a controlled environment, minimizing risks associated with nuclear propulsion systems. The planned trajectory for the test flight will cover altitudes between 435 and 1,240 miles above Earth. The mission aims to collect vital data on the performance of the nuclear thermal engine and its capabilities, setting the stage for future crewed missions to Mars. Industry collaboration and future outlook. In addition to NASA and DARPA, various industry partners are playing critical roles in the development of the nuclear thermal rocket. Lockheed Martin is responsible for the design and integration of the spacecraft, while BWX Technologies is tasked with constructing the nuclear reactor. This multifaceted collaboration highlights the importance of public-private partnerships in advancing space technology. The DRACO program is not only pivotal for Mars exploration but also for establishing a sustainable presence in space, including potential missions to the Moon and beyond. As NASA and its partners push forward with this technology, the implications for future space exploration are profound. The successful development and testing of a nuclear thermal rocket could pave the way for more ambitious missions, including deeper exploration of our solar system. Conclusion. The development of a nuclear space engine by NASA, backed by collaborations with DARPA and industry partners, represents a transformative step in human space exploration. With plans to test this technology by 2027, the potential to cut travel time to Mars to approximately 45 days is a game-changer. This advancement not only enhances the feasibility of crewed missions but also signifies a renewed commitment to exploring the final frontier. As the space community looks toward these upcoming tests, the excitement and anticipation for the future of interplanetary travel continue to build. The development of a nuclear space engine, specifically through NASA's demonstration rocket for Agile Cislunar Operations DRACO, presents several counterintuitive pieces of information that challenge common perceptions about space travel technology and nuclear energy. 1. Efficiency versus risk. While the concept of nuclear propulsion might evoke fears concerning safety due to the association of nuclear technology with disasters, the advancement of nuclear thermal engines is portrayed as a means to reduce astronaut risk. Shorter travel times from 7 months to approximately 45 days significantly decrease the duration of exposure to cosmic radiation and other space hazards, which could arguably make missions safer rather than more perilous, as one might intuitively expect. 2. Historical resurgence. The resurgence of nuclear propulsion technology after being shelved in the 1970s due to budget cuts might seem surprising. Many could assume that once a technology is abandoned, it remains obsolete. However, the ongoing advancements in materials and engineering, which allow for a new application of decades-old concepts, challenge the notion that past failures or discontinuations equate to permanent obsolescence. 3. Partnership dynamics. The collaboration between NASA, DARPA, and private industry may appear to represent a traditional approach to government-funded projects. However, the engagement of private companies such as Lockheed Martin and BWX Technologies suggests a shift towards public-private partnerships that leverage the agility and innovative capabilities of the commercial sector. This could imply that the government is moving away from a purely top-down approach which might have been assumed as the norm in such high-stakes technological endeavors. For a misconception of nuclear propulsion, there is a widespread belief that nuclear propulsion is primarily about the destructive power associated with nuclear weapons. In reality, the focus here is on peaceful exploration and the benefits of harnessing nuclear fission for propulsion. This duality of nuclear technology, potentially offering both destructive and constructive applications, illustrates the complexity often lost in public discourse. 5. Energy density. The claim that nuclear thermal rockets can be 3 times more efficient than chemical rockets may lead one to assume that their operational complexity is equally increased. However, the higher energy density of nuclear fuels means that these engines can achieve significant thrust without the need for large volumes of propellant, which defies the intuitive assumption that higher efficiency necessitates greater complexity or risk. 6. Logistical simplifications. The DRACO program's use of high-assay low-enriched uranium as fuel could be viewed as a more complex logistical challenge. However, it actually simplifies the fuel requirements compared to traditional rocket fuels. This approach highlights a counterintuitive aspect where the modernity of nuclear technology can reduce logistical burdens rather than exacerbate them. 7. Cryogenic challenges. The requirement to heat hydrogen to 4,400 degrees Fahrenheit while simultaneously storing it at -420 degrees Fahrenheit might seem counterproductive, suggesting a complexity that could deter the feasibility of nuclear thermal propulsion. Yet this is a necessary step that illustrates the innovative engineering capabilities being developed, which may lead to breakthroughs not previously thought possible. 8. Public perception of space travel. The prevailing narrative around space travel has often emphasized the heroic nature of traditional rocket launches, which rely on chemical propellants. The shift to nuclear propulsion may initially seem less glamorous or more intimidating to the public. Despite the significant advancements in speed and efficiency it offers, this challenges the assumption that public enthusiasm for space exploration is strictly tied to conventional methods. 9. Funding challenges. The concern regarding funding for nuclear propulsion technologies is a common one, but the partnership with DARPA and the involvement of multiple companies suggest a diversified funding model that may not have been available during past initiatives. This shift may be indicative of a broader recognition of the strategic importance of space exploration, potentially leading to more robust funding avenues than in previous decades. 10. Long-term goals. The focus on efficiency and speed for Mars missions may lead one to assume that this is a short-term project. However, the implications of developing a nuclear thermal rocket extend beyond Mars missions, as it could provide a foundation for future lunar and deep space missions, reinforcing the counterintuitive notion that immediate technological advancements can have far-reaching implications for humanity's long-term exploration goals. In summary, the DRACO program and the associated nuclear thermal rocket technology highlight numerous counterintuitive insights about safety, efficiency, collaboration, and the evolution of nuclear energy in the context of space exploration. These developments not only reshape our understanding of propulsion technology but also challenge deeply ingrained narratives about the risks and benefits associated with nuclear power. The report on NASA's initiative to develop a nuclear space engine, specifically the demonstration rocket for Agile Cislunar Operations DRACO, offers insight into the future of space travel, particularly regarding crewed missions to Mars. While much of the coverage emphasizes the potential to reduce travel time to Mars from several months to about 45 days, there are critical nuances and implications that are often overlooked. Key overlooked content and its significance. 1. Historical context of nuclear propulsion. The report mentions that the concept of nuclear propulsion dates back to the 1950s but was shelved in the 1970s due to budget cuts. This historical context is significant because it illustrates how technological advancements can be cyclical. Understanding the reasons behind the initial abandonment of nuclear propulsion can inform current debates about funding and public sentiment towards nuclear technologies. The resurgence of interest in nuclear propulsion backed by modern advancements in materials science and engineering indicates a shift in how society views nuclear energy, transitioning from fear to acceptance as a practical solution for space exploration challenges. 2. Technical challenges of cryogenic storage. There is a critical technical challenge noted regarding the need to heat hydrogen to 400 degrees Fahrenheit while storing it at -420 degrees Fahrenheit. This dual requirement poses significant engineering challenges that need to be addressed before practical applications can be realized. The complexity of this challenge is often understated, yet it highlights the intricacies involved in developing nuclear thermal propulsion systems. Overcoming these challenges is not only vital for the success of the DRACO program but also reflects broader implications for future propulsion technologies and spacecraft design. 3. Safety protocols and reactor activation. The plan for the reactor to remain off until the rocket reaches orbit emphasizes safety protocols, which is an essential aspect often glossed over in discussions about nuclear propulsion. This precaution is not just about safety, it underscores the need for rigorous testing and validation processes in developing new technologies. The safety measures are indicative of the lessons learned from past nuclear projects and reflect a more cautious approach to integrating nuclear technology into space missions. 4. Impact on mission logistics and astronaut safety. The reduction in travel time from 7 months to approximately 45 days has far-reaching implications for astronaut safety and mission logistics. Shorter missions reduce the psychological and physiological stresses on astronauts, which is crucial for their health and effectiveness. Additionally, the potential decrease in supplies needed for long-duration missions allows for more feasible mission planning and resource allocation. This point is significant as it directly relates to the viability of long-term human presence on Mars and other celestial bodies. 5. Collaboration with DARPA and industry partners. The collaboration between NASA, DARPA, and various industry partners like Lockheed Martin and BWX Technologies signifies a strategic approach to harnessing diverse expertise and resources for rapid development. This partnership model is significant because it reflects a trend in space exploration toward collaborative efforts that leverage both governmental and private sector capabilities. The implications extend beyond just this project. They set a precedent for future space exploration initiatives, emphasizing the importance of public-private partnerships in achieving ambitious goals. 6. Potential for Earth-to-Moon applications. While the primary focus of the DRACO project is on Mars missions, its potential applications for Earth-to-Moon transportation are noteworthy. This dual applicability suggests that advancements in nuclear thermal propulsion could facilitate not only deeper space exploration but also more efficient logistics for lunar missions. Understanding this broader application can influence strategic planning for lunar bases and other near-Earth missions, positioning the Moon as a stepping stone for further exploration. 7. Advancements in materials and engineering. The report mentions that recent advancements in materials science and engineering are enabling a new era for space nuclear technology. This point is often overlooked but is crucial for understanding the feasibility of developing reliable nuclear thermal rockets. Innovations in materials can lead to lighter, more efficient, and safer spacecraft designs, which could have wide-ranging implications for all forms of propulsion, not just nuclear. Conclusion. The initiative to develop a nuclear space engine is a monumental step toward enhancing human capabilities in space exploration, particularly for missions to Mars. However, the nuances and implications behind the technology's development, historical context, technical challenges, safety protocols, collaborative efforts, and potential applications are often overshadowed by the headline-grabbing reduction in travel time. Understanding these overlooked elements is essential for grasping the full significance of such advancements and their potential impact on the future of space exploration. The development of a nuclear space engine by NASA in collaboration with DARPA marks a significant advancement in space travel technology, particularly for crewed missions to Mars. Here are the 4 most valuable points for in-depth analysis and discussion. 1. Technological advancements and historical context. Nuclear propulsion technology has a rich history dating back to the 1950s. But it was largely abandoned in the 1970s due to funding cuts and changing priorities. The current push to revive nuclear thermal propulsion (NTP) leverages advancements in materials science and engineering that were not available during previous research efforts. This context is crucial for understanding both the potential and the challenges of modern applications of nuclear technology in space. Discussion points. How have technological advancements since the 1970s influenced the feasibility of nuclear propulsion? What lessons can be learned from past projects that were abandoned, and how can they inform current efforts? The transition from theoretical concepts to practical applications in nuclear space engines. What are the key milestones and challenges? 2. Efficiency and safety of nuclear thermal propulsion. The proposed nuclear thermal rocket engine is expected to be 3 times more efficient than traditional chemical rockets, reducing the travel time to Mars from approximately 7 months to around 45 days. This efficiency not only enhances mission feasibility but also plays a critical role in astronaut safety by minimizing the time spent in space, which is associated with various health risks. Discussion points. How does the increased efficiency of nuclear thermal propulsion alter mission planning for Mars? What are the specific safety measures being implemented to manage the risks associated with nuclear propulsion? How will reduced travel times impact the overall logistics of crewed missions to Mars and beyond? 3. Collaborative ventures and industry involvement. The DRACO program highlights significant collaboration between NASA, DARPA, and private sector partners like Lockheed Martin and BWX Technologies. Such partnerships are essential for pooling resources, expertise, and technology to accelerate the development of nuclear propulsion systems. They also reflect a broader trend in space exploration where public-private partnerships are increasingly common. Discussion points. What are the benefits and challenges of public-private partnerships in advancing space technology? How does collaboration across different sectors influence innovation and project timelines? What role do private companies play in the future of space exploration, and how might this change traditional models of government-led space missions? 4. Implications for future space exploration. The development of nuclear thermal propulsion systems is poised to redefine human space exploration not only for Mars missions but also for deeper space travel. The ability to access distant celestial bodies more efficiently opens new avenues for scientific discovery and potential colonization efforts. Furthermore, the technology may enable more complex mission architectures, including Earth-Moon transportation systems. Discussion points. In what ways could nuclear thermal propulsion facilitate deeper space exploration beyond Mars? What ethical considerations arise from the potential for expanded human presence in space? How might advancements in nuclear propulsion influence international space policies and cooperation? In conclusion, the advancements in nuclear thermal propulsion technologies signify a transformative shift in space exploration capabilities. The interplay of historical context, efficiency, and safety, collaborative ventures, and future implications presents rich avenues for discussion, analysis, and exploration of the potential of this technology. 1. Project Orion 1950s to 1960s. Project Orion was a study by the United States to create a spacecraft powered by nuclear pulse propulsion. The concept involved using a series of nuclear explosions to propel the spacecraft through space, theoretically allowing for rapid travel to distant targets like Mars. The project was initiated in the late 1940s and saw considerable development throughout the 1950s and early 1960s. However, it faced significant political and safety challenges as the technology involved would have required detonating nuclear bombs in the Earth's atmosphere. Ultimately, the project was cancelled in 1965 due to concerns about nuclear fallout and changing priorities in space exploration. 2. Nuclear engine for rocket vehicle application. NERVA 1960s. NERVA was a program initiated by NASA to develop nuclear thermal rocket engines for space missions. The program focused on creating a nuclear thermal rocket that would use a fission reactor to heat a propellant which would then be expelled to produce thrust. Testing of the engine was conducted in the late 1960s, and while it showed promise, the program was ultimately terminated in 1973 due to budget cuts and shifting priorities in NASA's mission objectives. Despite its cancellation, NERVA laid the groundwork for future exploration of nuclear propulsion technologies. 3. Mars Society's Mars Direct 1990s. The Mars Society, founded by Robert Zubrin, proposed a mission architecture called Mars Direct in the early 1990s. While not directly a nuclear propulsion project, Mars Direct suggested using available technologies including nuclear thermal propulsion to facilitate human missions to Mars. The plan emphasized a direct approach to send astronauts to Mars using in situ resources for fuel and life support. The concept helped reignite interest in manned Mars missions and highlighted the potential of advanced propulsion technologies, including nuclear options, to reduce travel times and costs associated with such missions. As NASA progresses with its plans for crewed missions to Mars, the development of a nuclear space engine through the demonstration rocket for Agile Cislunar Operations DRACO program signals a transformative leap in space exploration technology. This program, backed by a partnership with the Defense Advanced Research Projects Agency DARPA and various industry leaders, aims to demonstrate a nuclear thermal rocket engine by 2027. The implications of this technology are substantial, particularly in terms of reducing travel time to Mars from the current 7 months to just 45 days. Future outlook and predictions. 1. Acceleration of space travel. The nuclear thermal propulsion technology being developed is expected to fundamentally alter the dynamics of space travel. By enabling faster trips to Mars, it will not only shorten the duration astronauts spend in transit but also reduce the psychological and physical risks associated with prolonged space missions. This could lead to an increase in the frequency of crewed missions to Mars and beyond, effectively creating a more sustainable framework for human presence on other planets. 2. Increased mission viability. With shorter travel times, missions will require less food, water, and life support systems, making them more feasible and less resource-intensive. This shift could facilitate longer missions and the potential for more complex exploration tasks such as setting up habitats or conducting extensive scientific research on Mars. 3. Technological advancements in nuclear propulsion. The advancements in nuclear thermal propulsion technology are likely to spur further research and development in nuclear energy applications for space exploration. As NASA and its partners refine their designs, we may see innovations in reactor efficiency, safety protocols, and fuel technology, paving the way for advanced propulsion systems that can be utilized in other interplanetary missions. 4. Collaboration and investment in space technologies. The partnership between NASA, DARPA, and private companies like Lockheed Martin indicates a growing trend in collaborative efforts that leverage both governmental and commercial expertise. This could lead to increased investment in nuclear and other advanced propulsion technologies and encourage more private sector involvement in space exploration, enhancing innovation and reducing costs. 5. Regulatory and safety frameworks. The development of nuclear propulsion technology will necessitate the establishment of new regulatory and safety frameworks to address the unique challenges posed by nuclear reactors in space. As testing progresses, it will be crucial to ensure that protocols are in place to mitigate risks associated with radiation and reactor operations in orbit. 6. Strategic implications for space policy. The advancement of nuclear propulsion technology could have significant implications for national and international space policy. As countries recognize the potential of nuclear thermal engines for space exploration, we may see shifts in geopolitical dynamics, with nations competing to lead in space technology development. This could foster collaborations as well as tensions, especially in the context of lunar and Martian resource exploitation. 7. Long-term human presence on Mars. With the ability to travel to Mars in 45 days. The potential for establishing a long-term human presence on the planet becomes more attainable. This could lead to the development of colonies or research stations that support scientific endeavors and possibly pave the way for terraforming projects in the distant future. 8. Public interest and support for space exploration. Successful demonstrations of nuclear propulsion and subsequent crewed missions to Mars could foster greater public interest and support for space exploration. Increased visibility of successful missions and technological achievements may inspire a new generation of scientists, engineers, and explorers, driving educational initiatives and investments in STEM fields. 9. Broader impacts on space exploration technologies. The innovations spurred by the DRACO program could extend beyond human spaceflight to enhance robotic missions, satellite deployment, and deep space exploration. The technology developed could be adapted for various applications, including asteroid mining and interstellar missions, further broadening humanity's reach into the cosmos. Conclusion: NASA's initiative to develop a nuclear space engine represents a pivotal moment for space exploration. With the potential to reduce travel times to Mars and improve mission viability, the DRACO program could usher in a new era of human presence in space. As testing begins in 2027, the advancements in nuclear propulsion technology will likely reshape our approach to interplanetary exploration, influencing everything from mission logistics to international collaboration and safety protocols. The future of space travel may very well be nuclear, setting the stage for ambitious explorations beyond Mars and into the broader universe.